Hi, this is a video for the 6-7 notes, rectilinear motion with integrals. So we know now, and we've known for a long time, that if you have a position function, where this is the position of something that's moving back and forth in a straight line as a function of time, that the derivative of that with respect to time, dx dt, would be the velocity. And if you take the derivative of that, you get acceleration as a function of time. And now we know how to find antiderivatives, so we can reverse this process. If you found the antiderivative of acceleration, that would get you back to velocity, and the antiderivative of velocity gets you back to position. And if you want to ground this in the context of other types of problems that we're more familiar with, we know now that if you're looking at the graph of the derivative of a function, there's an awful lot of information that you can get from that graph. And likewise here, if you think of position as being like the original function, velocity would be the first derivative. There's an awful lot of information you can get if you have a graph of velocity versus time. And the most important thing to realize, to understand, is that if we do take the definite integral, so from some time to some other time, of velocity with respect to time, then fundamental theorem of calculus tells us all we need is an antiderivative of this, right? Antiderivative of velocity is position. And then we just need to plug in those values. So we would get position at time 2 minus position at time 1. And that is just change in position. You could call it delta x if you want to. And that's displacement. And if you're in physics class, also, you know that that's obviously a very important thing. But even if you're not, we've seen this already. We know that this is an important concept. This is the difference in the ending position and the starting position. Now, we could also can find, if we want to know the total distance that something has traveled, total distance something has traveled, well, we only want to consider speed instead of velocity here. In other words, we want to just take the absolute value of this and make all those values. And you know what? I should not have put that. My absolute value signs included too much stuff there. There we go. That's better. We can take the integral of the absolute value of velocity, and that will give us, instead of displacement, that gives us the total distance traveled. The bad news about that is that we don't really have any way of dealing with finding antiderivatives of things inside absolute value functions. But there is more good news coming about that soon. So although this is a concept, that's a useful concept, in terms of what we can do analytically, we would still have to find this absolute value function, break it up into a piecewise function, and deal with it one piece at a time. So it's an important idea, but analytically it's not really particularly user-friendly. Okay, a couple more quick things. Notice also that if you had an acceleration function and you integrated from time 1 to time 2, that would give you, well, the antiderivative of acceleration is velocity, so that would just give you the velocity at time 2 minus the velocity at time 1, and that's the change in velocity if you want to write it like that. So with these three things, you can also, if you're wondering, is there an analogous thing that you could do by throwing absolute value signs around this? The answer is not really. There isn't really any meaningful thing that we do with anything else except for the velocity. So there isn't this total distance traveled. This concept really just applies to distance. There isn't like a total amount of velocity change or something like that. There is not an analogous thing to do with this. It just happens at this level. And when we, in the next chapter, when we take this concept and we extend it into other different kinds of contexts that aren't just physics, motion back and forth, we'll find that this total distance traveled is really something that's very specifically applied to this kind of problem. Right, so given those three things, we just also want to notice that if you wanted to find the average velocity is change in position over change in time. And now we have a way of defining that with an integral. So since change in position or displacement is this, we could say that your average velocity, if you wanted to do it this way, sometimes it's convenient to do it this way, you could do that integral divided by your time interval, delta t, time 2 minus time 1, if you want to write it like that. And average acceleration is equal to change in velocity over change in time. And change in velocity, well, that's the integral from time 1 to time 2 of acceleration over the time interval. Can you see all that there? Yeah. Okay, so let's just do a couple example problems. I'm going to do a couple of problems from the book. These are in-between problems that you're going to do tomorrow. So 6A, let's see, we have in part A, which I already wrote the A, didn't I? The velocity of some particle is given to be 1 plus sine of t. And they're telling us, our book uses S for position. We won't usually do that. In other places, like College Board problems and problems that your teacher makes up, it'll probably be X instead of S. So when the book says S, that's their letter for a position function. I'm going to use X. I'm just going to change it to that. And they're telling us that the position at time 0 is equal to -3. And the directions say, use the given information to find the position function of the particle. So how do I do that? Well, position is the antiderivative of this. So the position function is equal to the antiderivative of this, which would be, let's see, the antiderivative of 1 would be t. The antiderivative of sine would be negative cosine t. And then I haven't put in any value yet, so I have to put the plus c here because I don't know what it is yet. But now I know that at t equals 0, the position is -3. So I can plug those values in to find the c. So it looks like I have -3, cosine of 0 is 1, plus c, so it looks like c is equal to -2. So my position function, the antiderivative of velocity, t minus cosine t minus 2. So just looking back at what we did there, you could not have found the actual position function without knowing some position at some time. If you know some position at some time, then you can solve for c, and you can come up with a position function. All right, in part B of that problem, they're giving us an acceleration function. And let's see, it's t squared minus 3t plus 1. And they're giving us a couple pieces of information. The velocity at time 0 is 0, and the position, I'm going to write it as an x instead of an s, is also 0. Right, so you could call this the initial velocity, right, at time 0. The initial velocity is 0, the initial position is also 0. Okay, so antiderivative of acceleration is velocity. That would be t cubed over 3 minus 3t squared over 2 plus t, there's my antiderivative, plus c. Then I can use this. I know that the velocity is 0 when t is 0, and so it looks like this is just a polynomial, so my c is just going to come out to be 0. So that means my velocity function is t cubed over 3 minus 3 halves t squared plus t. Right, the c came out to be 0. And I'm going to, just to avoid any confusion, I'm going to put a little c1 on that, because now I'm going to take the antiderivative of velocity. That will get me back to position. So that's t to the 4th over 12 minus 1/2 t cubed plus t squared over 2 plus c, and since again this is a polynomial, when I plug in the 0, 0, c is going to come out to be 0. And I should call this c2, right? So these are not the same c. They both happen to come out to be 0, but that was just by chance. So my position function is t to the 4th over 12 minus 1/2 t cubed plus t squared over 2 plus 0. So I'm just going to leave that off. Right? There you go. Well, those are sometimes called initial value problems, where you're finding an antiderivative and then solving for c. All right, another type of problem that we can do here using this idea of displacement, total distance traveled. Do 10a, and I'm going to show you a few calculator things that we can do here too. We don't use our calculators a lot of the time, but problems like this, we often deal with pretty messy velocity functions. Oftentimes they are not analytic. In other words, you can't find, no matter how clever you are, you can't find the antiderivative of them using any of the rules that we know. So in that case, you have to use your calculator, not just because you want to. So we're going to try to find here, they're giving us on the time interval from 0 to 2, and they would like to know, find the displacement and the total distance traveled. All right, so I know that displacement is equal to the integral 0 to 2 of the velocity function, which in this case is 3t minus 2 dt. That's how we find the displacement, right? Integral of the velocity function. So let's see, that would be the antiderivative of this, which would be 3/2 t squared minus 2t from 0 to 2. Plug in the 2. So that's 3/2 times 4 minus 2 times 2 minus, when I plug 0 into this, it's just a polynomial, so that's all going to be just equal to 0. And that's, let's see, 6 minus 4 is 2. So the displacement is 2. And I want to point out to you, thinking about the last problems that we just did on the previous page, that here, when I found this antiderivative, I didn't need to know what the plus c was. Remember, same issue that we dealt with when we first looked at the fundamental theorem. When I subtract these two things, the C is wherever this thing started, whatever that initial position might have been, it doesn't matter if all I care about is the displacement. I don't ever know where this thing was, but I know that the difference between when it started and when it ended is 2. In other words, the displacement is 2. Right? I like to use the example of if I were to call you up and say, hey, I just drove 50 miles north on Interstate 81. Well, you would know that, right? You'd know that I drove 50 miles north, but you would have no information about where I started and where I ended, only that I went north 50 miles. So here, this is the same. This displacement here tells us that this thing went in the positive direction 2 units. Where did it start? Where did it end? We have no idea. But if we only want the displacement, then that's good enough. In part B, in the continuation of part A, they want the total distance traveled. Total distance. And to do that, we have to do 0 to 2, the absolute value of the velocity function. And this isn't a really super hard one. You can see that that 2/3 would be the t-value where it goes from negative to positive. You could make it piecewise and break it up into 2 integrals. If you want to see what that would look like, it would look like, well, we could go 0 to 2/3, and then it'd be 3t minus 2 dt, and just make sure that I take the absolute value of that piece, and then here I'd go from 2/3 to 2, and then just make sure that I take the absolute value of that piece and then add them together. That's pretty time intensive, and that's what you'd have to do even with a simple one like this, right? Every place where it changed from positive to negative, you'd have to break up this interval. And typically, we're not going to do that kind of thing by hand. So I'm going to show you now how to do it with your calculator. I'm going to do it with both types side by side so you can see what it looks like with the old calculator and with the new calculator. All right, so first thing I'm going to show you is how to do it, graphing, and I'm going to show you with the first one. So I'm not going to do the absolute value thing. I'm just going to try to get the answer. We know that this one's supposed to be 2, so I'll show you how to get that from your calculator. So I'm going to put in 3x, here's my velocity function, minus 2. And I'll do it on this one too, 3x minus 2. Go ahead and graph. And then if you go to your calculate menu, second, go to calculate. If you look at the bottom choice, look at that. The integral from f of x dx. What? You ever see that before? It's been there all the time. So we'll bring that up. It's going to ask me for a lower limit and then the upper limit. So lower limit, we want to go here from 0 to 2. I'm redoing this problem here. So from 0 to 2. Oops, and then I made the answer go away. And look, it actually shades it in. It shades in the area that you're doing. How cool is that? I'm just going to do it again real quick. So second calculate, I want to do the area from 0 to 2. And it tells us that that area is 2. Pretty cool, huh? Now, we can also do that. We go back to y equals. I can insert, I'm going to go second insert. In the math menu, if you go over to number, the first thing there is absolute value signs. On my old school calculator here, it just does absolute value and then parentheses. It looks like this one. It actually gives you those. So 3x minus 2, and then I'll delete the rest of this on the outside. So they actually look like absolute value signs. That's nice. I could just look at the graph again, and you can see now all the part that was negative gets bounced up there, and then I can do again, second, calculate the area from 0 to 2. Oops, that's a 3. Sorry, 2. And it shades it in for you. Okay, now really super important thing for you to notice here is that correct answer here is actually 10/3, or 3.3 repeating. So what's this garbage here in the calculator? It says 3.3338416. What? Well, the calculator, these things don't know how to do calculus. So when you ask it to do something like this, it's really doing a Riemann sum. It's doing an approximation. And the methods that it uses to do that approximation are pretty good, but you need to recognize, if it gives you something like this, you need to recognize, you smart human being, that this is 3 1/3, right? If you see some kind of repeating decimal and then something weird happens at the end, it's because of the method the calculator's using. So please be aware of that. Right? If we were copying this down for a College Board answer, would be wrong in that decimal place. Would say 3.334, but here it's not 3.334, it's really 3.333. So you just have to be careful. When they're really messy functions that we don't know how to do this way anyway, we just have to trust what the calculator tells us. Okay? All right. Now, let's see, what else was I going to show you? Oh yeah, on the home screen, so second quit. Here, if you just wanted to enter this, I'll just do it with this one here and show you the 10/3. Just like with derivatives, if you only wanted to find this integral, you can go math, and then scroll down to, it's number 9, fn int. That means give me a numerical approximation of an integral, number 9. On the old school calculator, we could enter here, I want to do the absolute value of 3x minus 2, comma x, that's like the dx, comma 0, comma 2. So the syntax is the function you want to take the integral of, comma x, that's like the dx from 0 to 2. So this thing that I've entered in my calculator here represents this. Right? On the new fancy calculator, I'm going to do the same thing. It's the same place in the menu, Math 9, but look at that. It looks just like the integral. So we want to go 0 to 2. My function is, I want absolute value of 3x minus 2. Oops. 3x minus 2 dx, and then we'll try that with those, and gives me the same wrong answer, but it did, interestingly, compared to the graphing method, it did give me a little bit more accurate answer. So I don't know what that's about. I don't know why it's different, but it is interesting. So there you go. There's how you can do, and then, you know, any number of problems you do in the homework, you could check like this, but of course, you know, there's going to be lots of no calculator problems on assessments. So that should get you through. That's what you need to know about integrals and rectilinear motion. So velocity function, lots of information to be had there. All right.